Welcome, curious minds. Today we're diving deep into the intricate world of database management systems, or DBMS.
Yep.
You've handed us a great set of resources, including some really sharp interview questions. Our mission isn't just to, define terms, it's to unpack the core concepts, revealing why data management works the way it does, and hopefully give you a true shortcut to understanding this critical field, maybe at a deeper level.
Exactly. These aren't just definitions you memorize, they're the fundamental principles. The rules governing how nearly every piece of digital information you touch daily is meticulously stored, accessed, and secured.
Right.
So yeah, we aim to extract those crucial nuggets of insight, help you connect the dots, and grasp the strategic importance behind these foundational elements.
Okay, let's unpack this then. Our journey begins with establishing a robust understanding of the system itself.
Right, the basics.
Then we'll build up to some truly nuanced details about how databases handle complexity, ensure unwavering accuracy, and even, recover from the brink of disaster.
Sounds like a plan.
So, to start, most of you probably know a DBMS is the software backbone managing our data. But it's not just a storage unit, is it?
No, not at all.
It's like the gatekeeper, the librarian, security chief, all rolled into one.
That's a good way to put it.
Can you elaborate on the most significant advantages of relying on such a system? Beyond just, raw storage, why do we opt for a DBMS over, say, a huge pile of linked spreadsheets?
That's a crucial distinction, yeah. The advantages are truly significant, especially thinking about how things evolved from simple file systems. First, data integrity. A DDMS rigorously ensures your data is accurate and consistent. It prevents those weird discrepancies that could lead to, financial errors or just unreliable reports.
Okay, accuracy. Makes sense.
Then data security. It provides really granular, controlled access, so only authorized users see sensitive info. That's non-negotiable these days, right, with privacy concerns.
Absolutely correct.
You also get efficient data retrieval. These systems are engineered, really optimized to find information incredibly quickly, even in vast, petabyte-scale data sets.
Wow.
And a huge one is reduced redundancy. By enforcing structured storage and what we call normalization, we'll get into that, a DBMS minimizes duplicate data, vital for efficiency and consistency.
Avoids having the same info in 10 different places.
Exactly. And for peace of mind, there's robust backup and recovery, built-in mechanisms to protect against data loss, paramount for, business continuity.
You need that safety net.
Definitely. And finally, concurrent access. Multiple users, multiple applications, all interacting with the database simultaneously without conflicts, without messing each other up. It's the cornerstone of almost every modern system we use.
That concurrent access point.
Ah.
Yeah, that highlights a key challenge modern systems face. And it leads us perfectly, I think, to a distinction that often causes confusion. DBMS versus RDBMS.
Ah, yes.
For our listeners who already follow the topic, what's the fundamental architectural shift that R really implies?
Right. That R for relational, it is indeed the game changer. A DBMS, the broader term, it's really any system designed to manage data. This could include older models like hierarchical or network databases, maybe even simpler systems that don't enforce strict relationships. Think early file systems, or maybe some NoSQL databases fit here too.
Got it. The general category.
Exactly. An RDBMS, though, is a subset of DBMS. It specifically implements the relational model. This means data is organized into tables with really meticulously defined relationships between them. It leverages primary and foreign keys to enforce integrity, and it relies on SQL, structured query language, for querying. The brilliance of the relational model, which Edgar F. Codd proposed, lies in its mathematical foundation that brings unparalleled consistency, flexibility, making it the dominant way we handle transactional data worldwide.
So it's that structure, the relationships, the mathematical rigor that sets the RDBMS apart.
Precisely.
Beyond the relational model, just for context, can you quickly outline the other major types of DBMS? Maybe touch on their historical context or where they might still be used.
Sure, yeah. For a broader perspective, historically we had hierarchical DBMS. They structured data in a stripped tree, like parent-child model. IBM's IMS is a classic example. Good for fixed, rigid relationships.
Like an org chart.
Kind of, yeah. Then came network DBMS. A bit more flexible, a graph-based model allowing many-to-many relationships. Integrated data store, IDS, was one. But they could get quite complex to manage.
I can imagine.
More recently, object-oriented DBMS emerged, tried to store data as objects, aligning more closely with object-oriented programming.
Okay.
But while these all have their niches, the relational model's balance of structure, flexibility, and that powerful query capability, it just means it remains central to our discussion today. It's still king for a lot of applications.
All right, so if RDBMS is king and it uses tables, let's quickly solidify those core building blocks. We all kind of know tables, rows, columns. But what truly defines a relation in the RDBMS context? Why is that specific terminology significant?
Good point. We do tend to say table casually, but in proper relational theory, it's a relation. And the significance is that a relation adheres to strict mathematical properties. It's not just a grid.
Ah, okay. More formal.
Right. Each row, or tuple, as it's formally called, represents a unique entity, a specific product, a single customer. Each column or attribute represents a distinct property of that entity, product name, price, description, whatever.
Standard stuff.
But the crucial part is the schema. That defines the table's structure, column names, data types, and, importantly, the constraints that maintain data integrity. That mathematical basis ensures consistency and predictable behavior. That's critical.
And central to that integrity.
Yeah.
Keys, primary keys, foreign keys, they sound like the absolute backbone.
They absolutely are.
Could you not just define them, but maybe illustrate their role with an example? Something that really brings home their importance for keeping data consistent.
Definitely. Keys are like the glue and the guardrails of the relational model. Can't build without them. So a primary key, it's a unique identifier for each record, each row, within a single table. It cannot be NaLel, it has to be unique. Guarantees you can pinpoint any single record without ambiguity.
Like a student ID number.
Exactly, or a product ID in a products DS table. Product ID would be the primary key, ensuring every product has its own distinct identifier. No confusion.
Okay, and the foreign key.
Right. A foreign key is an attribute or a set of attributes in one table that refers to the primary key in another table. This is what creates the relationships between tables.
The link.
Yes, the link. And crucially, it enforces referential integrity. This means if table A references table B, the data it's referencing in table B must actually exist and be valid. So, if an orders table has a product ID foreign key, it ensures you can't create an order for a product ID that doesn't exist in the products TS table.
Prevents those orphan records.
Precisely. Prevents orphan records, maintains logical consistency across the whole data set. It's fundamental.
That concept of referential integrity.
Yeah.
Yeah, that really clarifies it. Now, you also hear about candidate keys and super keys. How do these fit in? How do they relate to the primary key? What's the hierarchy?
Right. It's all about different levels of uniqueness. A superkey is basically any set of one or more attributes that can uniquely identify a row in a table. It might include extra unnecessary attributes, though.
Okay, like more than you need.
Yeah. For example, in an employees table, maybe employee, first name, last name, together could uniquely identify someone. That's a superkey. But employee ID alone is probably enough.
Got it.
So a candidate key is a minimal superkey. It uniquely identifies a row with no redundant attributes. Employee ID would likely be a candidate key. Maybe social security number could be another candidate key in the same table. A table can have several candidate keys.
Multiple options.
Exactly. And the primary key is simply the specific candidate key that you choose to be the main identifier for that table. The one the database uses by default for relationships, for indexing. Your chosen champion, basically.
The chosen champion among the unique identifiers.
Yeah.
I like that. This leads us nicely to keeping that data pristine, clean, normalization. What is it and why is it such a critical concept for long-term database health?
Normalization is, well, it's a systematic process. You structure your data to reduce redundancy and improve data integrity. It usually involves breaking down large, complex tables into smaller, more focused ones, and then establishing clear relationships between them using those keys we just talked about.
Breaking things down?
Yeah. And it's critical because it, one, eliminates data redundancy, avoids duplicating information, which saves space, sure, but more importantly, it prevents inconsistencies. If you change a customer's address, you only want to change it in one place, right?
Right, not hunt it down everywhere.
Exactly. Two, it prevents anomalies, update, insert, delete anomalies. These are weird side effects that can happen if your data is poorly structured. You might accidentally delete information you didn't mean to, or struggle to add new data correctly. And three, it just generally enhances data integrity and consistency. It makes sure the database remains a reliable source of truth, makes it more adaptable to changes, easier to maintain over time. It's good database hygiene.
So building a robust, tidy, efficient system makes sense. But then there's this concept of denormalization.
Yes.
That sounds completely counterintuitive, like we're intentionally undoing all that good work we just did. How do we make sense of that? Why would you add redundancy?
It does sound backward, doesn't it? But that's where the architectural decisions get really interesting, and it often comes down to performance. Denormalization is the strategic introduction of redundancy, often by combining tables back together or duplicating certain data fields. But it's done intentionally to improve query performance.
Where to speed?
Exactly, for read speed. While normalization is fantastic for transactional systems databases where data is frequently updated, inserted, deleted, and integrity is absolutely paramount.
Like order processing or banking.
Perfect examples. Denormalization often shines in read-heavy environments. Think data warehousing, reporting systems, business intelligence. You might accept a bit of controlled data duplication if it means a complex report query that used to take minutes now runs in seconds because the database doesn't have to join 10 different tables anymore.
Okay, so it's that classic engineering trade-off again.
It absolutely is. Integrity and update efficiency versus read speed.
That makes perfect sense. Speed versus integrity.
Yeah.
But, for listeners thinking about real-world scenarios, how do you even begin to decide when that trade-off is worth making?
Yeah.
Are there specific, red flags that scream denormalize here or stick to strict normalization?
That's a great practical question. You generally stick to strict normalization religiously, as you said, when you have high write volumes, complex business rules that need enforcing, and those strict consistency requirements. Banking, order processing, inventory management, places where every transaction has to be perfect.
Right.
You consider denormalization when you're building analytical systems, data marts, reporting databases, where the primary use is reading data, running complex queries, aggregating information. Performance for those reads becomes the priority. A big red flag for maybe needing denormalization. A frequently run critical report that requires joining, say, 10 or more large tables, and it's just agonizingly slow.
Yeah, I can see that.
At that point, creating something like a pre-joined summary table or maybe a materialized view, which is a form of denormalization we can touch on, becomes very, very appealing.
Yeah.
You take the performance hit up front, maybe during off-peak hours, to make the reads fast.
That's a great practical insight. So speaking of ensuring data quality, these rules you mentioned, they're formalized through constraints, right? What are these database police keeping everything orderly?
Constraints, yeah. They are the explicit rules built right into the database schema. They limit the type of data you can put into a table, fundamentally guaranteeing integrity and consistency. They are absolutely foundational.
So what are the common types?
Well, you have not null. Pretty simple, ensures a column can't be left empty. Like a user's email address probably shouldn't be null.
Makes sense.
Primary key, which we've covered. Unique identifier also implicitly enforces not null and unique. Foreign key. Links tables ensures that referential integrity. Make sure a bookid in a borrowings table actually points to a real bookid in the books table.
Prevents those orphans again.
Yep. Unique. Ensures all values in a column are distinct, different from each other. But unlike a primary key, it can allow one NL value, typically. Useful for things like ensuring username is unique.
Okay.
Chico. This lets you define a specific condition that values must satisfy, a Boolean expression. You could use it to ensure, say, salary is always greater than 0 or that order date is not in the future.
That's custom rules.
Exactly. And default. Assigns a predefined value if you don't provide one when inserting a new row. Like a status column might default to pending automatically. These constraints work together to automatically prevent bad data from ever getting into your system in the first place.
Right, they're the built-in guardians. Okay, so once our data is structured, constrained, protected, the next step is actually using it, getting information out.
Free.
How do we pull out meaningful insights? Find that one specific record. That's where SQL really comes into its own, right?
Especially the select statement.
Precisely. The select statement is, the lingua franca of data retrieval in the RDBMS world. It's how you ask the database a question and get a precise answer back.
How does it work?
Well, you can retrieve specific columns by naming them or grab all columns using select. You can filter results using where clauses, like where sales amount 1,000. You can sort the results using order by, maybe order by order date, day of C for newest first.
Okay.
And crucially, you can combine data from multiple related tables using various join operations. Inner join, left join, etc. It's an incredibly powerful and flexible tool for getting anything from a simple list to a complex analytical report.
And to make those answers come back faster, especially with lots of data, we often use something called an index.
Yes, indexes are key for performance. Can you explain what an index is? And maybe for our listeners, what's the key difference between a clustered and a non-clustered index? That comes up a lot.
Sure. An index is essentially a performance optimization technique. Think of it like the index at the back of a textbook. It's a special lookup structure that the database uses to speed up finding data. Instead of scanning every single row in a huge table, which is slow, a full table scan, the database can use the index to quickly locate the specific rows that match your query criteria.
Okay, like a shortcut.
Exactly. Now, the difference. A clustered index actually determines the physical order of the data rows on the disk. The table data itself is sorted according to the clustered index key.
So the book itself is sorted that way.
Pretty much. Because the physical rows can only be stored in one order, a table can only have one clustered index. Often, it's on the primary key.
Makes sense. And non-clustered.
A non-clustered index is a separate structure. It contains the index key values, and for each key, it has a pointer back to the actual data row in the main table. It's like having separate indexes in the back of the book, one by author, one by subject, all pointing to the same page number.
So you can have multiple of those.
Exactly. You can have multiple non-clustered indexes on a single table, each optimizing searches on different columns without changing the physical storage order of the data itself.
That's a really powerful optimization. But I've heard that having too many indexes can actually slow things down sometimes.
Yeah.
Like it becomes a performance drain itself. Is there a point of diminishing returns?
Oh, absolutely. You've hit on a critical point there. While indexes are fantastic for speeding up reads, select statements, they introduce overhead for writes, so insert, update, delete operations.
Why is that?
Because every time you change data in the table, the database also has to update all the relevant indexes to keep them synchronized. If you have 10 indexes on a table, one insert might require 11 writes, one to the table and one to each index.
Ouch.
So yeah, too many indexes, especially on tables with high write activity, can definitely hurt performance overall. The art of indexing is finding that sweet spot, indexing the columns frequently used in where clauses and join conditions, but not over-indexing. It involves analyzing query patterns, monitoring performance. It's a balancing act.
Yeah. Thoughtful optimization again.
Yeah.
And what about views? We touched on them briefly. Our sources talk about views versus tables. What's the fundamental difference in how they function?
The key difference really is physical storage. A table is a physical structure. It stores data directly on disk. Rows, columns, occupying space.
Okay, the real data container.
Right. A view, however, is virtual. It doesn't store data itself. Instead, it's essentially a stored query definition.
A saved query.
Exactly. When you query a view, the database looks up its definition, runs that underlying query against the base tables, and then presents the results as if they came from a table.
I see.
So views are excellent for simplifying complex queries. You hide the complexity behind the view. They're great for security. You can give users access to a view that only shows specific columns or rows they're allowed to see. And they help abstract away underlying table changes without duplicating data. Very useful.
Okay, let's shift gears slightly to managing changes. There's a really crucial distinction between delete and truncate in SQL. It sounds small, but it can have huge implications.
Yeah.
What should our listener absolutely know about these two?
Oh, this is a fundamental one. Get this wrong and you can lose a lot of data very quickly. Delete. This command removes specific rows from a table, usually based on a where clause, like delete from orders where order status can't...
False. Selective removal.
Right. And importantly, each row deletion is logged by the database in the transaction log. This makes delete operations transactional and rollbackable. If you make a mistake, you can usually undo it within a transaction. The downside, this logging makes delete potentially slower on very large tables.
Right. Safety have a cost. And truncate.
Truncate. This command removes all rows from a table, period. But it does it very differently. It usually works by deallocating the data pages used by the table rather than deleting row by row.
Much faster then.
Much, much faster, especially for huge tables because it involves minimal logging. But here's the critical catch. Truncate operations are generally not rollbackable within a transaction in the same way delete is. Some systems might have ways back, but typically once you truncate, that data is gone. Instantly, permanently.
Wow. Okay. So delete for precision, for safety, maybe when you need to undo. Truncate for speed when you are absolutely positively sure you want to wipe the entire table clean.
That's the perfect summary. Use truncate with extreme caution.
Good advice.
Ugh.
This raises an even more critical concept tied to that rollback capability. Transactions. We hear commit and rollback. Why are these the invisible guardians of trust in pretty much everything we do digitally?
They really are. They're not just technical terms, they are the absolute bedrock of reliability in databases. Commit and rollback are central to database transactions. A transaction is a sequence of operations treated as a single, indivisible, logical unit of work.
All or nothing.
Exactly. That's the atomicity part of ACID, which these enable. Commit permanently saves all the changes made during the current transaction, all the inserts, updates, deletes to the database. Once you commit, those changes are durable, they're permanent, they survive crashes, and they become visible to other users or transactions.
Okay, save for good.
Right. Rollback, on the other hand, reverses all changes made during the current transaction. It effectively undoes everything done since the transaction began, restoring the database to the state it was in before you started that unit of work.
The undo button.
The ultimate undo button for a set of operations. Together, commit and rollback ensure those ACID properties we mentioned. Atomicity, all or nothing, and durability, once committed, changes survive failures. Imagine transferring money. You debit one account, credit another. Without transactions, the debit could succeed, but the credit fail.
Leaving money lost in limbo.
Precisely. Commit and rollback ensure that both operations succeed together, or neither happens. They guarantee the integrity and reliability of every digital interaction, from online shopping to banking. They are fundamental.
That's a powerful way to frame it. Okay, but what happens when lots of people, maybe thousands of users or processes, are all trying to access or change the same data at the same time? How does a DBMS handle that intense concurrency without everything just breaking down into chaos?
Concurrency control. This is where things get really complex, but also really clever. It's a huge area of database science. DBMS employs sophisticated techniques to prevent conflicts and ensure data remains consistent and correct, even when many transactions are running concurrently.
Like what?
The most common mechanism is locking. Transactions acquire locks on data items they need to access, maybe a shared lock if they just want to read it, or an exclusive lock if they need to modify it.
So others have to wait.
Exactly. An exclusive lock prevents anyone else from reading or writing that specific piece of data until the lock is released. Shared locks allow multiple readers, but no writers. This prevents interference, but it can lead to contention where transactions are waiting for locks and potentially deadlocks where two transactions are waiting for each other.
The dreaded deadlock.
Yep. So managing locks efficiently is key. Another approach is timestamp ordering. Each transaction gets a unique timestamp when it starts. The DBMS then uses these timestamps to ensure that operations happen in a logically consistent order, as if they ran serially based on their timestamp. If a conflict occurs, say a newer transaction tries to read data, an older transaction hasn't committed yet, the system might roll back the newer one. Then there's optimistic concurrency control. This approach basically assumes conflicts are rare. Transactions just go ahead and do their work without acquiring locks first. Then, only before they try to commit it, the system checks if any conflicts did occur while they were running.
Checks at the end.
Right. If a conflict is detected, the transaction is rolled back and has to be retried. It can be very efficient if conflicts truly are rare, but if they're common, you waste a lot of work on rollbacks.
Trade-offs again?
Always trade-offs. And finally, you have protocols like two-phase locking, 2PL. This is a specific, robust locking protocol designed to guarantee serializability, meaning the concurrent execution produces the same result as some serial execution order. It has a growing phase where transactions acquire all the locks they need, and then a shrinking phase where they start releasing them.
Yeah.
It's effective, but needs careful implementation to manage deadlocks.
It really is like a sophisticated traffic controller for data, managing all these simultaneous movements without collisions.
That's a very good analogy.
But even with all these safeguards, systems fail. Hardware breaks, power goes out, servers crash mid-operation. What happens then? How does the database pick up the pieces? How does it recover? And what role does that transaction log play in this seemingly impossible task?
Yeah, recovery is absolutely critical. Imagine a massive enterprise system processing millions of orders and boom, the power grid fails. Without robust recovery, it would be chaos. Financial data lost, orders corrupted.
A nightmare.
Exactly. That's where the unsung hero, the transaction log, comes in. It's essentially a persistent sequential record, usually kept on separate storage, of every single change made to the database by transactions. Every insert, update, delete, every commit, every rollback, often including the data values before and after the change. It's like a meticulously kept journal of everything that happened.
The database's diary.
A very detailed one. If there's a system crash, when the database restarts, it uses this log to perform recovery. First, it can roll back any transactions that were in progress but hadn't committed when the crash occurred. It uses the log to undo any changes they made, ensuring the database doesn't contain partial, inconsistent results. Atomicity again.
Okay, clean up the unfinished business.
All right. Second, it can redo any transactions that had committed, but whose changes might not have been fully written from memory buffers to the main data files on disk yet when the crash happened. It uses the log to reapply those committed changes, ensuring durability, no committed data is lost.
Making sure what was saved stays saved.
Exactly. The log allows the database to restore itself to the last consistent state, usually the point right before the crash, ensuring data integrity even in the face of disaster. It's the ultimate safety net.
That's an incredible mechanism for resilience. Okay, finally, let's briefly touch on one more performance enhancer we kind of alluded to earlier with denormalization. Materialized views. How do they differ fundamentally from the regular views we discussed, and where do they really shine?
Right, materialized views. They are distinct because, unlike a regular view, which is purely virtual, just a stored query,
The definition.
yes, just the definition, a materialized view actually stores the results of its query physically on disk, like a real table. It's essentially a pre-computed cache or snapshot of the query's data.
So it holds the actual data?
It holds the actual results, yes. While a regular view reruns its query every time you access it, a materialized view gives you instant access to its stored results. Of course, that data can become stale.
Needs updating.
Exactly. The materialized view needs to be refreshed periodically, maybe on a schedule, or when the underlying base tables change to keep its stored data up to date. But the benefit is dramatically improved performance for accessing complex, frequently queried data.
Where would you typically use them?
They really shine in data warehousing, business intelligence, reporting systems, places where you need lightning-fast access to aggregated data like complex summaries or pre-joined tables. Think of a monthly sales summary report. You can materialize that view, refresh it nightly, and users get instant results during the day instead of waiting for a complex query to run every time.
Makes a lot of sense for those reporting scenarios.
Wow, okay.
We've covered a huge amount of ground today, from the fundamental architectural differences between DBMS and RDBMS to the really intricate ways databases handle concurrency, ensure data integrity with keys and constraints, and even recover from catastrophic failures using logs.
Yeah, and hopefully you've seen how concepts like relational theory, normalization, ACD properties, transactions, locking, these aren't just abstract academic terms. They are highly practical, strategic mechanisms. They ensure the reliability, the efficiency, the trustworthiness of the digital data systems we absolutely rely on every single day. Understanding these nuances, I think, moves you beyond just using a database to really comprehending its inner workings and the critical design choices made under the hood.
So what does this all mean for you, our listener? Well, you now possess a far more robust understanding, hopefully, of how information is organized, managed, safeguarded in our incredibly data-driven world. This deeper knowledge is invaluable, really, whether you're facing a technical interview, preparing for a critical business decision that relies on data, or maybe just satisfying that curiosity about the hidden engines driving technology.
And maybe for a final thought, something to mull over. If traditional relational databases are so brilliantly designed for structured, consistent data, what new challenges do you think the absolute explosion of truly unstructured data poses?
Like social media feeds.
Exactly. Social media, vast sensor networks from IoT devices, even open-ended content from generative AI. How do these core DBMS principles, consistency, structure, transactions, how do they hold up?
Or do they need to change?
Right. How might those principles still apply, or perhaps need to radically evolve to meet these entirely new kinds of demands?
That is definitely something to ponder as you encounter data out there in your own world. Thanks so much for joining us for this deep dive.